We're here to talk about building and managing container images at scale with cloud-native Buildpacks. And when I talk about scale, I mean companies that need to build hundreds of thousands of container images a day. Companies like Heroku, Salesforce, Bloomberg, Google Cloud Run, for instance. I'm Terence Lee. I come from Austin, Texas. Work at Heroku as one of the architects on language things as well as other stuff, and help co-create Buildpacks way back in the day, and am now a maintainer on the Cloud-Native Buildpacks project, which we'll be talking about in this talk. And here's my colleague Manuel, who comes from Cologne. He's actually the Java and JVM languages owner who owns all the things. So if you have any problems with Java on the platform, he's the person that you complain to about it. But he's written most of the code that we'll be demoing today in our talk. Slides. This is a sponsored session from Heroku, so I'm glad you came to our paid talk instead of any of the ones that actually submitted talks that got into DevOps. And for those of you who don't know, Heroku is one of the early PaaS pioneers, a cloud platform that lets companies and individuals build, deliver, monitor, and scale applications in one of the fastest ways that you can go from idea to code to the URL on the web, bypassing kind of all those infrastructure headaches and reducing kind of cognitive load that you'd get from doing all those things. And since this is a company thing, I feel like they always like to see all the people in attendance. So if you don't mind, I'm going to take a selfie on stage with all you so we can see. Awesome. Thank you all for indulging with me there. Okay, so now onto the actual talk here. Enough of the fluff. So this talk split up into kind of 4 acts. We're going to talk about Buildpacks if you don't know what they are. We're going to see a live demo with Manuel, or a demo with Manuel of like all those things in action. Move on to what it looks like to actually operate and do things with Buildpacks once you have it out in the wild, because actually building a thing is only the first step. You then inherit it forever. And then kind of the rest of the Buildpack ecosystem, so you don't have to kind of deal with this from scratch. So I thought I'd start out with a little bit of history, just to show that Buildpacks weren't a thing that we just built and kind of shipped. It's actually been around for a long time. We started in open source Buildpacks back in 2011 at Heroku, where we were actually a Ruby-only platform, and this was kind of the transformational point where we went from a Ruby-only platform to a polyglot platform by extracting all of our language-specific bits into these kind of modular composable things that we eventually called Buildpacks. You could build Java apps on the platform in addition to Ruby, Node, etc. Right? And it was received well enough that other companies and projects like Cloud Foundry actually adopted that as part of their ecosystem. So anyone who's used Cloud Foundry, PCF, things like that, you've probably have used Buildpacks. But they've actually forked the API that we had, and we added things, and so we actually diverged paths of like Buildpacks that weren't really compatible with each other. So we had this forked ecosystem. And as part of kind of the whole container movement, we decided to join forces and wanted to bring all these things that we learned over the last like decade plus of running these things in production on behalf of customers to this cloud native container ecosystem, right? So instead of targeting proprietary artifacts, we actually cloud native Buildpacks build 2 OCI images, and we end up building cloud native Buildpacks. It joined the CNCF as a sandbox project in 2018, and we're now an incubating project. CNCF being the Cloud Native Computing Foundation. So simply, Cloud Native Buildpacks is a tool that takes your application source code and transforms it into an OCI image that you can run with and push to registry without the use of Dockerfiles. And it creates a well-structured OCI image that has layers that map logically to your application instead of kind of the bespoke things that are random commands that you decide to run. And what it brings to the table are modular. These Buildpacks themselves are modular and composable and encapsulate a specific technology, right? So I can have a Buildpack that is for Java, right? Encapsulating all the concerns, what it means to like build a Java application. I can have one for Node. I can have one specific to even like Maven or Gradle, right? So the granularity of what we want there. And so what that brings to an organization is the ability for us to separate kind of roles and responsibilities instead of continually shifting everything to the left. So everything's just not a platform problem. And so, for instance, as an application developer, by leveraging these build packs that are specific to Java and are shareable, that I don't need to be artisanally copying and pasting stuff into Dockerfile to build out my own build pipeline. I can leverage this Java build pack that these build pack authors have built who are potentially like the SMEs in your organization who know how Java should be built in your app, in your organization. And so they can build these shareable units that I can use as an application developer, right? And kind of on the platform developer side, I was mentioning that Buildpacks are composable, and one of the big benefits of that is you actually can reduce significantly the number of base images that your organization needs to maintain and use. And so at Heroku, for instance, we have a single Heroku 24 base image that's based on Ubuntu 24. But like, let's say you're using RHEL 9, right? Like, it's really common in organizations to see like, I have my RHEL 9 base image, my RHEL 9 with Java, my RHEL 9 with Node.js, and if I need to use like Java and Node.js, there's like a third base image that's like the combination of both of those things. And so this composability of build packs, the build packs themselves are actually the ones that are contributing these kind of runnable artifacts and things into the image. So the platform operators get to focus on just delivering the platform side and not having to kind of construct and build all these other things. So achieving this organizational efficiency so we're not continually shifting everything to the left, as we saw in the keynote. And so, that's a bunch about just like what we get from organizing things with build packs, but like we're talking about scale and you got to be able to do things quickly and fastly. So instead of just telling you how it's going to go, Manuel is going to show you how we do that with build packs.
Thank you, Terence. So hi, everyone. I will give you that little hands-on Terence was talking about to show you all the things that he spoke about in action so you can see how it works in practice. So I have 2 demo apps here that would serve as our stand-in for like a whole fleet of applications. And this talks about scale and how CNBs can help you with that, but I obviously don't have time to juggle more than 2 apps here on stage. Both applications are simple Hello World apps. One is written in Spring Boot, one is written in Micronaut, and the applications themselves aren't that important for the demo, really. Okay, let's say we want to deploy all of our apps to a container runtime going forward. We want to make sure that we actually run the build inside a container as well, so we can run the builds on a local developer machine or on CI. And I will write a Dockerfile for both applications and then build them with CNBs so we can compare the 2 approaches. So I will start with the Spring Boot app. As you can see here, it uses Maven and has a wrapper file here, which is great. Let's look at the Docker file that you might write for an application like this. So here we use Heroku 24 as the base image, which is basically Ubuntu 24. We copy all the contents into the image, then install OpenJDK for that application, and then run Maven wrapper with the correct Maven goal for the framework that we use. In this case, it's install, and then specify the run command if we spawn a container with this image. That should be run. Okay, let's kick off the build for this. It will take a moment to download OpenJDK and then build our application with Maven. I don't think there's much to explain here. You've probably all seen this before. So since we have a second here, I want to be transparent. I pre-recorded all of this demo in my terminal before this talk, and I'm playing it back right now. There are many moving parts in this demo, and a spotty network connection, or even more likely me messing something up, would put a stop to the demo. So I didn't want to risk that. What is also a benefit of having this recorded is that I can just skip time and our build is done. Great. Now we can start a container with that image to quickly verify that it did what we expected it to do. We also expose port 8080 here to the local machine. Let's look at the log files for it. A Spring Boot app, amazing. Let's make a curl request. And it says, hello DevOps from Spring Boot. Cool. So that worked. I will now do the same thing, but with a slightly different app. That's the Micronaut app I've been mentioning. Looking at this directory listing, we can see that it is Micronaut, and it uses Gradle instead. So the Docker file for this would look very similar to the Spring Boot Docker file that we just saw, but there are differences, right? I use, obviously, Gradle wrapper instead of Maven wrapper. I use shadow jar as the task that I want to run with Gradle, which is Micronaut specific in this case. And also the run command for the application is different. Since building this will take a moment, let's kick that off. And while this is building, I want to explain the point of this part of the demo. I want to show that having specific Docker files for each app doesn't really scale well. The apps and the maintainers of those apps are different. Like one team might have a Dockerfile wizard at hand, just waves the wand, and then suddenly the changes are there. Another team might have not and have trouble making simple changes. And if we need a change to all the builds in the organization, then we also need to organize that change throughout the whole organization, which will take a lot of time. And as we can feel now, running a build takes time. So if I mess something up, I need to fix it, run it again, fix it, run it again, until I have a working image. So as software developers, I think the solution to that kind of problem is second nature. We write reusable code for it. That code can then be written by domain experts that know how to actually build Java applications correctly. We can have integration tests for it in a central location. And should ever a bug slip through, which will happen, we all know that, we can fix it in that central location and roll it out to everyone. I will time travel again. That's fun. And then go through the motions to verify again that our image works. We need to do that because the rest of the demo will build up on top of these images. So I want to show you that they work. Log file shows the Micronaut app, and our HTTP request unexpectedly works because this is pre-recorded. I will now show you how this works with Cloud Native Buildpacks. At the core, the Cloud Native Buildpack project maintains specifications for all the Buildpacks themselves, but also the platforms that they run on. And I here just showed you the pack command, which is a reference implementation of such a CNB platform. So you can see here it has available like some subcommands, for example, build, which will take your application source, as Terence mentioned, and turns it into an OCI image. There's config, where that lets you configure various aspects of pack itself, and also builder. And a builder, in a nutshell, is a collection of build packs and base images that define how your applications are being built. That's the mechanism that centralizes the whole build into this opinionated build pipeline across all of our apps. And you can create your own builder if you want, if you have specific requirements, or you can use one that already exists from the ecosystem. And we can use the same pack command and ask it, what builders do you suggest? So as you can see here, we have a builder from Google, we have multiple ones from Paketo, and the best one of all, that's our own from Heroku. We will use that for the demo, obviously. It supports many language ecosystems. For Java, we support building your app with Maven, Gradle, or SBT. And we also support multiple architectures in ARM64 and AMD64. I will now configure Pack to use that builder as the default. So now the interesting part, how does it look like to build an application with CNBs after I've configured this? I will just run pack build, give it an image name, and the path to the application. That's all I really need to do here. Pack will now go through the builder and ask all the build packs in it if they can build this application and which other build packs they need to fulfill that request. And we can see here in the detect phase that it detected that it is a Maven app. We know that. But we also need OpenJDK, so that's what the Heroku JVM Buildpack will provide to run both Maven and our application. Note that we didn't configure anything here. Like the detection process was fully automatic. We didn't say this is a Maven app, build it as a Maven app. It knew. The warning that you see after this is also a great example of what Buildpacks can do beyond just building your application. The Buildpack detected here that we didn't explicitly specify the OpenJDK version that we want to use for our application. And that's not really a problem or an error, but we want to remind users that they should set the OpenJDK that they need for their application. So we output this neatly formatted error message, warning message, I should say, with instructions how to actually set the OpenJDK version. And then we see that here's the actual installation of OpenJDK, and it also detected that this application uses Maven wrapper instead of just a POM XML. So the Buildpack saw that and runs Maven wrapper instead of installing Maven for you. We think applications should use Maven wrapper, but we also don't want to fail the build if there's no Maven wrapper to make it easy to get started with our Buildpacks. If your organization is more strict and wants to enforce Maven wrapper, you can enforce it in your own Buildpack easily. Cool. Let's scroll past all of this dependency downloading. Let's try the build image the same way we did with the Dockerfile images. Again, exposing the port so we can make an HTTP request. Looking at the logs. That's our Spring Boot app. And that's our HTTP request. For the Micronaut app that uses Gradle instead of Maven, the process is exactly the same. It's the same command. We just run pack build, give it an image name, and the path to the application, and off we go. So we can see here that it detects Heroku Gradle instead of Heroku Maven. And we get the same nice warning message because that comes from the shared OpenJDK Buildpack that both of our builds uses. It will also detect the correct task that we need to run in Shadow jar, and it also knows how to actually run a Micronaut application. So Buildpacks can be implemented in almost any language, and that allows us to implement complex logic, like determining which framework this application uses, or parse command output from Gradle, for example, or dynamically branch out into different build processes. We are not limited by a somewhat rigid step-by-step recipe like Dockerfiles are. Cool. I think this is my final time travel for today. And we will verify that this image works. Here's our Micronaut application, and HTTP also works. So should policies ever change? Let's say we want to use OpenJDK cables from a specific vendor because we now have a support contract with them, right? We can enforce this at the builder level and immediately roll out the changes to all future builds. Let's say I have 1,000 apps, all with Snowflake Dockerfiles. How long would that take to change across the whole organization? Next, I want to talk a little bit about efficiency and more specifically caching. So if we build many apps, saving build time and storage will add up quickly at scale. So how does caching work with Dockerfile? If I rebuild the app again with Dockerfile, we would see that most of the layers are actually cached. So that's kind of neat, but there are some problems with this. I will now add a README file to this application because it previously didn't have one, and then we'll rebuild the app again. So reinstalling OpenJDK doesn't really seem to be necessary after the change that I just made. But that is what Docker is doing right now. It will also kick off the Maven build again, and will also re-download all the dependencies, which is kind of wasteful. So why is that? When we work with Dockerfiles, we have to be very careful about the order of operations. Some of you probably have spotted this issue earlier when I showed you the Dockerfile. And I lied. This is my final time traveling. Let's look at the Dockerfile. So every instruction in this file is cached separately in its own OCI image layer. So you can imagine these layers like git commits. They store only the delta between the previous file system state and the next one. So if Docker determines that a cached layer for one of these commands is stale, it will rebuild that layer and all the layers that come after it. So in this case, I have the copy instruction here, and that was invalidated by adding the README file, and everything afterwards was re-executed. So of course, I could just move copy a little lower. That makes sense to not rebuild OpenJDK every time I just add a README file. But you have to know about all these intricacies of Docker files across the whole organization again to make that easy. So if I rebuild the same app with Pack after adding my README file, you would see it doesn't suffer from the same problem. That is because CNBs have fine-grained control over the image layers and how they are cached. So if I scroll up a little bit, you can see that it does rerun Maven, but all the dependency download is not there. And that's because the Heroku Buildpack pre-primed and restored the old local Maven repository for us. And we do rerun the build because adding a README file could change the build, right? We could like put it into a jar file or something. But our dependencies we clearly can reuse as well as the OpenJDK. Another example of how CNBs can be smart about caching is the OpenJDK version. In the Dockerfile example, the layer that stores OpenJDK itself will never be invalidated by itself. So if no other layer that comes before will invalidate it, we will not get a new OpenJDK version if a new critical package update comes out. The Heroku JVM CNB will, before restoring an already cached OpenJDK version, check if there's a new minor version and then discard the cache. There's another caching aspect I want to talk about. Remember when I said that layers are just deltas of file system changes? Every layer has an associated hash that is very similar to a git commit ID. So if two images use the same layer to compose the final image, that layer is only stored once. When you have a central registry like Docker or Amazon's ECR, that layer will also only be transmitted once. And at scale, that adds up. And I wouldn't be standing here and telling you about this if there isn't a problem with the Dockerfile that we wrote earlier, right? So before I can show you the problem, I need to extract some metadata from our images. I use a tool called dive here that is really handy if you want to know more about the contents of your Dockerfile layers. So that takes a second. And I will now look at the JSON file for the Spring Boot application. And this is our OpenJDK layer, the second to last. And you can see that the hash starts with EAAC7. And if I look at the same file for our Micronaut application, that hash is different. It's CBU14. Even though both layers were created with the exact same command at pretty much the exact same time. And that means that that OpenJDK layer will not be shared across all of our application. In this case, 2, but if you have 1,000, that is really a problem. So let's get the same metadata for our CNB images and see how that differs. So here, the layers look a little different. That is because they were created by a Buildpack. This is the OpenJDK layer here, and the hash starts with 4377. And for Micronaut, pretty much unsurprisingly here, it has the same hash, as you can see here. So why is this difference between like the Dockerfile build layers? The hash of a layer is determined by the contents of it, but not only that, but also the file metadata. So one example would be file creation dates or file access dates. And the CNB lifecycle will change or set that metadata to a specific value so that we have these reproducible caches. Another benefit of this behavior are reproducible builds. So if we have the same builder and the exact same application image and run the build twice, both images will be a byte-for-byte replica. All right, everything I demoed so far becomes even more important when we add another language into the mix. So it's not uncommon to have like a server-side application in the front end that use a different set of technologies. But that would amplify all the problems we just talked about. For example, if I add a bunch of Node.js-related stuff on top of my Docker file, if we change anything about the front end, we will invalidate all the caches of the back end. And for sure, we can make trade-offs and move the thing that changes the least to the top of the Docker file, but we will end up with unnecessary rebuilds regardless. So CNBs were designed with this use case in mind. I have a super simple Node.js-based project here that I will use to demo this. All it does, it compiles this less file into CSS, uses some variables, and calculates tau for us. The package JSON for this application is also pretty simple. It just specifies the dependency to the less compiler as a def dependency, and then in the build script, it will compile our less file into CSS. So I will copy now the contents of that front-end app into the Spring Boot app that we had before, and then we'll tell Pack to rebuild that image again. Note that I pass Heroku Java and Heroku Node.js explicitly here. That is to ensure that the order of build is what we expect. And again, this output is very similar to the things we have seen before, but again, Maven was detected as before. It detected that we use NPM and not Yarn, for example, for front-end stuff. And we also see that OpenJDK is not being reinstalled. It is being reused from our earlier demo, as well as the Maven caches. And after the Maven build comes all the Node.js stuff. Cool. So that Spring Boot app I showed you earlier is written in a way so that it will respond with the build CSS file if it's there. So let's make a request to that and see if that worked. We now know Taos. Amazing. And I want to pivot away from efficiency into security at scale. Let's say we have thousands of apps. And some nice morning, you just got your coffee, and then there was a serious security bulletin about OpenSSL that we use in our base image. So we need to quickly patch all of our images. And that is where we run into a problem, because we need to rebuild all of them. And the caching problem I alluded earlier to applies here as well, because as the base image changes, all the subsequent layers will be invalidated, right? So we have to rebuild all of our applications that might not even build anymore. And that's a terrible situation to be in when time is at the essence. And CNBs provide a solution to that problem. They allow us to rebase an already built image onto a new base image without requiring a rebuild of the application. The process itself isn't really that complicated, and my Git analogy that I had earlier for layers still holds here. So like you can rebase a Git commit onto a new base, you can also rebase a layer onto a new base image. The CNB specification dictates the build packs where they can write files and when they can write them. And that ensures that there will be no conflicts ever. So you can do this with all images. There's also a constraint that the base image, the old one and the new one, need to be ABI compatible. But that's the case for many Linux distributions if we stay on the same major version. So let me show you how this works. Let's stop the container from the previous demo. And use this long command that basically just runs dpkg and prints the OpenSSL version that we have in our Spring Boot CNB image. It is 0.3 at the end. That's the important bit. And now I can use pack rebase to rebase that image onto a new base image that is updated. With pull policy always, I tell pack that it should look for a new base image if there is one. Of course, this demo was crafted specifically, so every time we built earlier, I built with an outdated base image, so we can actually see a change here. This would take a little longer than it usually does in production because of Docker daemon, but it should be done quickly. Nice. So let's run that command again. And we can see now that the OpenSSL version now ends with 0.4 without needing to rebuild the app. And I think that's pretty cool. And that CNB rebase process is built on a practice that we at Heroku have proven by doing for like millions of apps over more than 10 years. We rebase actually all of our customers more than twice a month to keep their apps up to date without them needing to rebuild their apps, of course. Yeah, and that's really the end of my demo. I will now hand it back to Terence to go a little deeper on security and CNBs. Take it away.
Awesome. Thank you, Manuel. Yeah, so kind of building off of rebase, for me, I like diagrams to kind of picture what this actually looks like. And so, we were talking about rebase, and it really looks like this lift and shift where we're taking the existing layers and moving them on top of the new base image. And the important thing to know is actually that the digests for those app layers don't change, right? So we are getting a new app image digest, and a new, obviously the new OS layers that we've introduced, but we aren't changing the app layers because we're not doing a rebuild at all. We're just, we're just creating a new image with basically new OS layers, and that will be important in a second when we talk about deploying and rolling this out. In the demo, we were showing a single app, but Manuel kind of alluded like, what does this look like in a real organization where you probably are managing not a single app, but hundreds or thousands of applications? What do you do when that CV comes and hits your company and you have to deal with it, right? And so, with Dockerfile, of course, that's the first line in your Dockerfile, so you're losing all that cache. I think the best case scenario is you just have to do a rebuild, right? But the worst case scenario, since you're doing a rebuild, there's like side effects and other things, and you are actually running the entire build pipeline, like depending on how old or whatever your application is, like the worst case is that it might actually build successfully, right? And you have to actually go around and tinker with it. And so you're saving massive time by doing a rebase since you're not doing rebuilds. And more importantly, once you have those images and you roll them out, like let's say I'm deploying back to the same node, right? I just have to push those new layers, like the new OS layers. The app layers are already there. and I just push that JSON manifest of that OCI image. That is that new image, and then I'm good to go, right? If I'm running multiple pods on that single node, that, again, we were talking before about minimizing the number of base images that I'm having in my organization, I am just pushing those OS layers and now just JSON text for each one of those for that one node, because the app layer's already there on that node, because I didn't have to change any of those digests. So I'm able to boot those apps up fairly quickly. And as you scale that across an organization, that becomes significant savings versus, if you're doing this with Dockerfile, all those digests are going to change for every single layer in your app. So you're literally pushing an entire image and every single layer in that image as you roll that out, right? And so as we talk about environmental sustainability and efficiency, the most sustainable and efficient thing you can do is actually just not having to do compute at all, right? So with CNB, we're able to kind of achieve that at a scale in an organization where we have to roll these things out both efficiently and quickly. But enough about rebase. One of the other things that we get when we start talking about Cloud Native Buildpacks is talking about software supply chain security, and probably most specifically the build part. And so when we talk about software supply chain security, right, like we're talking about how we can ensure the thing that you're building on your computer is the thing that actually is running in production, hasn't been tampered with, and so customers can actually, that are using it, like aren't getting something that is unintended when they're running with it, right? And I feel like this really came on the map back in 2020 with like the infamous SolarWinds hack, where it impacted, it was estimated like 18,000 computers across a minimum 100 organizations, including even some like U.S. government agencies like the Pentagon, places that take security pretty seriously, right? And this was just like through a routine software update. And it wasn't a thing that, we just sat and did nothing with, right? And so the governments did respond. Across the pond with the White House, they, passed Executive Order 1428 to basically improve cybersecurity across the nation, instituting policies and practices that you're required to do to work with the government and basically do those contracts, both like government agencies as well as government contractors, right? So requiring things like software bill of materials, multi-factor authentication, all these kind of practices to ensure simply better cybersecurity practices. In addition to that, even in the EU here, we've passed the EU Cyber Resilience Act to protect both businesses and consumers. And one of the fun facts I think that came up at the time is they estimated that in 2021, cybercrime would amount to about 5.5 trillion euros. It's a good number of zeros there as we think about that. But that didn't end in 2020. Software supply chain attacks have been on the rise kind of ever since and grown massively, right, as a really important attack vector for dealing with inside of organizations. So if it's not something you're thinking about already, it probably is something you should be thinking about. And like I mentioned, Buildpacks really help with kind of the build threat side as we kind of split these into the various threats in software supply chain security. And so, we spent a lot of time talking about how we get reproducible builds, you get to standardize things in an organization, and so that really helps a lot with ensuring that you're getting this consistency as you're building your application, right? Like you want to take your source code and ensure the thing you get out at the other end is going to be the thing you expect, and then as you need to either roll out policies or practices, like manual reference, changing the JDK, those kind of things can happen in a singular place, and you don't have to do that across your entire organization. So that helps out a lot. In addition, like each individual build, like as you're either doing debugging or other things, like you're able to build this build infrastructure that you can rely on that helps you kind of standardize how everything is built inside your company. And then not only the building, but also actually like having transparency of what you're running in production, right? So I feel like as Java developers, most people are very familiar with the Log4Shell incident that happened a few years ago, kind of dealing with those securities. Like the first step to address it is to know what is actually vulnerable in production that is running that kind of dependency. So software bill of materials, there's two major formats that people are using widely. That's SPDX and CycloneDX. As part of CNBs, the specification, we're not trying to be kingmakers. We support both of them. And so having this file be built alongside your build, you're getting this transparency of like what is actually in that image that you're running. So you can see like components, dependency, licensing. You can have licensing policies, right, to ensure, I'm not running GPL code if that's not a thing your company wants to do. The exact versions you're running, the authors, the digest, things like that. And so you can get this programmatic way, commonly either JSON or XML of that thing. I was talking with someone that was doing some SBOM stuff, and they literally handed me a PDF document that was like 1,000 pages. Like, good luck, parsing and reading, figuring stuff out, being handed a document like that. So that's why these formats exist. And one thing that's really important is like, if you're familiar with this, you probably have looked at potentially like image scanning tools like after the build. And in the community, I think it's been well regarded that the best time to actually do this is not after the image has been built, but to do it at build time, right? Like these build packs and doing it at build is the place where we've actually put these dependencies into your image. So we know exactly what was put in and where we got those things. And so you can ensure like that's the stuff that ends up in that spawn. But not only that, but also you toss away all the build tools oftentimes because you don't want them in your production image. And you can also build a separate build SBOM as well. So you can see also like, has there been attacks on other things of the tools that were used to actually build that resulting image? And so it's important to kind of get both of those things. That's enough about kind of operations and things. We're, I guess, running close on time here. So pivoting to the Buildpack ecosystem a little bit. So to get started, the easiest way is a bunch of stuff that Manuel's demoed has been through Pack. It's available through Homebrew as well as many of the Linux package managers, including apt and other things. You can also always just head to the actual project page, github.com/buildpack/pack, and check any of the releases and kind of download any of the artifacts there. And you just run a pack build, right, on your images, easy as Manuel showed off. That's probably the best way to get started. We've referenced other builders, mostly showing off the Heroku Buildpacks. We like to think they're the best, but obviously you have other options here as well. You don't have to create Buildpacks to get started on your own. I think, in fact, most people don't, right? Like, you want to just take your Spring Boot app that you have and run Pack against and try it. Like, you can go off and do that, right? And so a lot of organizations that are getting into Buildpacks or even have run into production don't build their own unique way of building Java. What they do is they take one of these existing things, vet it, run that through their security team, et cetera, and then just augment and kind of build it. So they're not in kind of the game of having to rebuild their entire Java pipeline and figure out how to do that. Outsource it to people who it's their jobs to do that all the time. And then you can kind of supplement the existing build packs and builders that are out there. In addition to that, there's also other Buildpack platforms that actually execute and run on the whole Buildpack lifecycle. And so we've spent a lot of time obviously talking about Pack. That's like the local CLI one. It's a local CLI one built against your Docker or Podman. And honestly, like the easiest way to get started is just to run it like in your Jenkins or whatever pipeline. We actually provide specifically a GitHub action that helps you get Pack installed, and you can use that to keep it up to date. And in fact, we use it on our own Heroku Buildpacks as part of our own testing tool chain, as part of those automations there, as well as the upstream Cloud Native Buildpacks project too. We also provide a Circle CI orb for those who are using Circle. If you are using Tecton for CI/CD, there's a Tecton template that's provided by the project as well. If you're using Kubernetes, we actually have Kpack as a Kubernetes operator that handles both the build side as well as kind of all the rebase stuff. And so it will detect changes in your repo and other things and kind of kick off builds for that. And as Java developers, if you're using Spring Boot, there is Buildpacks built into Spring Boot itself where you can actually containerize your Spring Boot app and you don't even need Docker, right? So it's like built into thing. If you haven't tried that out, I'd recommend checking that out as well. So in closing, hopefully you've seen how Buildpacks can help your organization scale, not only through build efficiency, but also the ability to kind of standardize how your build practices are done throughout your organization through kind of that separation of roles, helping us not continually shift everything to the left to that platform team, and allowing the folks that are specialized in the various things to actually like do that piece of the work of the problem space. We're all like sharing those roles and responsibilities there. And in addition, we're also able to help deal with some of these operational concerns, right? Because day one is just where we start getting that app image up, but like having to maintain and operate this stuff is really the bulk of the work of releasing applications into production. So if any of this stuff was of interest to you, buildpacks.io is the homepage for the upstream CNB project. We're on the CNCF Slack in the Buildpack channel. You come talk to us there. Have a Twitter account. Hit us up on GitHub as well. And we are also proud sponsors as Heroku. Come say hi to us at the booth. Please go and try Pack. You can run through the demo like through your own Spring Boot app. Super simple. Get started today. And thank you. And we have stickers. I know everyone loves stickers. So come say hi. Come ask us for stickers. Happy to chat more. Thank you. So I think we have 8 minutes or so if people have questions. Sorry, it's a little hard to see with Shani, but I see a hand raised.
I have a question. Is it possible to define a spectrum of, if for instance, Java versions? For instance, if I sit in an organization where I'm interested in security, then I say I can live with from 0.3 to 0.5, but you are not allowed to use 0.2. Is that possible?
Not with our Buildpack, because we support the customers on the platform and want to have like a broad spectrum of like LTS available versions and stuff. But if you want to enforce that for your organization, you have your own OpenJDK Buildpack, and you can do really whatever you want, really. It could be, if your version is divisible by 2, then it's allowed. That's pretty easy to implement. So I guess the answer is yes. Yeah.
Yeah, it's not. Just to repeat the question, I think it was asked like, is there a way to basically enforce like specific JDK versions because that's like what your policies for your organization is. Yeah, I think with the Heroku one, we try to, like Manuel was saying, we support basically what's supported by kind of the upstream project. I know like on the Paketo side, this is actually a common thing. So I think in their buildpack.toml, they actually specify the different JDKs that you can run. But one of the things I was mentioning about composability is that like, yeah, you can build your own kind of open JDK and then Buildpack that basically does that bit, and then you can insert it into and then leverage the rest of kind of the Buildpack pipeline. So you don't have to build out like what it means to use Maven or whatever, and so you can just do that part of it. So that's actually like a common thing we do on the Salesforce side actually for internals, is like there is a Salesforce JDK, and so we leverage the Heroku Buildpacks for stuff, but we actually have to ensure that people are using the correct version of Java. Cool. Well, I don't see any other questions, but folks who, you're welcome to come down and chat with us if you want to have private stuff, and then we'll also be at the booth too, so come swing by our booth as well, or come get stickers. Thanks, Al.